morning. So Neil Armstrong had very rightly said, that's one small step for man, one giant leap for mankind. Good morning, respected Professor Vinay Gupta, Professor, Department of Physics and Astrophysics, University of Delhi, Professor Binay Kumar, Professor, Department of Physics and Astrophysics, University of Delhi, Principal, Deshbandhu College, Dr. Rajiv Agarwal, Teacher in Charge, Physics Department, Dr. UP Tyagi, Coordinator, DBT Star College Scheme, Dr. Indrakant Singh, Coordinator, IQAC, Dr. Aditya Saxena, Department Coordinator, Physics DBT Star College Scheme, Dr. Ajay Pratap Singh Gehlot, Organizing Secretary, Dr. Kakoli Bera and Ms. Manju Rani, Convener, Physics Society, Dr. Pankaj Singh, and all my co-coordinators of Physics Department, DBT Star College team. On behalf of Physics Department, Deshbandhu College, I, Deepti Goyal, in the festive atmosphere of Holi and Easter, welcome all the distinguished guests at the 2 days national seminar on the recent trends in contemporary physics under the aegis of IQAC and DBT Star College scheme in online mode. I also welcome all the resource persons and all the participants who have showed their interest in our 2-day seminar series. Before starting today's session, we shall have a virtual ceremony of lamp lighting and Saraswati Vandana as a tribute to Goddess Saraswati. So I take this opportunity to express my heartiest thanks to Professor Vinay Gupta and Professor Binay Kumar, Professor, Department of Physics and Astrophysics, University of Delhi, for their guidance and encouragement. I also express my gratitude to our principal, Dr. Rajiv Agarwal, for his support, guidance, motivation, and encouragement. Physics is really nothing more than a search for ultimate simplicity, but so far, all we have is a kind of elegant messiness, as said by Bill Bryson. So certainly, this seminar on recent trends in contemporary physics will be fruitful and beneficial in coming out of this elegant and exchanging new ideas about the current scenario technological changes prevalent in the society, discussing the research on important development in physics, including the purview from industrial and technological advancement. Now I request Dr. UP Tyagi, Teacher in Charge, Physics Department, to brief about the 2-day national seminar. Over to you, Tyagi sir.
Sir, you are on mute. Uday sir. Uday sir, your voice is not coming. Uday sir, you.
I think there is some network issue with Tyagi sir. So I request our esteemed, dynamic, active, our own principal sir, Dr. Rajiv Agarwal, to kindly formally welcome our August gathering. Dr. Rajiv Agarwal sir.
Rajiv sir, are you there?
Okay, sir, he is not. Okay, sir. Dipti ma'am.
Anji.
Sir has joined, but now he is not in meeting.
Okay.
There's some network issue, I think.
Okay.
Uday sir, can you check your audio once again?
Can you hear me?
Yes, we can hear you, sir.
Yeah, I take this opportunity to welcome our distinguished guest, Professor Vinay Gupta, Professor Binay Kumar, and Professor Vijay Kumar. You see, it is a matter of pride for me to associate myself in organizing this workshop, which, we had been waiting for a long time. At the very outset, I would like to make it clear that, we are not organizing this workshop just for the heck of organizing a workshop, a national seminar. See, why I am saying this is that is because, the seeds of this national seminar were sown maybe 4.5, 5 years ago. If I take you back in time, especially Professor Vinay Gupta, he must be remembering, in case he is able to recollect, that he was invited for a talk by Dr. Ajay Pratap Gehlot, maybe about 5 years ago. And we had in our interaction during that time in the principal's room, he gave us a suggestion that, you must have a nano material lab. And if you are going to work in that direction, I will offer all my assistance in establishing this lab. So, as everything, this national conference, this national seminar also has a past, a present, and a future. The past I've already discussed. It was, Professor Vinay Gupta. Right now, he is a member of our governing body also. And that time in our discussion, when he had come, again, in an IQAC meeting, again, we had a discussion about it. And since that time, the department is working in that direction. So, along with that, maybe during that time only, our young, dynamic coordinator DBT, Star College Project, Dr. I.K. Indrakant, was about to submit the project in the DBT. And maybe after a few days, we got the information that the project has been sanctioned. Now, this was a point of glitter in my eyes, that, we'll be able to purchase few equipments of technically importance, especially relating to this particular lab. So, and very rightly, we started working in that direction. After that, our new principal, again very young and dynamic principal, who joined, he extended all help for establishing this lab in the college, and we are in the process of developing this lab in the college. So, and we thought that probably first of all we are going to do our homework before conducting such a seminar. Right now, the title of the seminar is to emerging scenario or emerging in contemporary physics. But I think the title should have been the emerging trends in contemporary experimental physics, because in this national seminar, all our invited guests are eminent scientists, especially in the field of experimental physics. So what I mean to say is that we have really worked for it. We waited patiently for it. And, we wanted to organize an offline national seminar on this topic, which would have been highly inspirational to the students as well. But since because of the academic, we could not organize this, and I thought we should not, wait further any longer in conducting this seminar. Before, conducting this seminar, we had organized a workshop on vacuum coating, sputtering, and thin film deposition techniques. That was organized on 22nd and 25th, where, we had made a demo. We checked and demonstrated the deposition of a thin film by vacuum coating, thermal evaporation vacuum coating. So basically, what I feel is that if you are able to demonstrate experiments which are of crucial importance in inciting the scientific temper to the students, then they are able to correlate with the syllabus that is being taught to them, and we are able to correlate with the experimental techniques with the students also. Time and again I have had discussion with Professor Vinay Gupta when he was involved as a convener of syllabus framing committee, restructuring committee in CBCS format. And there again, I found that the kind of dedication he has for his lab, especially for the students and inciting, the scientific experimental temper for the students, he can really motivate the students once the lab is, established in the college. And in the process, we are able to purchase few equipments which are again of quite importance to the lab. We have purchased, to quote some of the few, surface plasmon resonance setup and vacuum coating units. These are, very costly equipments, and still, as a result of cooperation from our young scientist, Dr. I.K. Singh, we have been able to purchase these. We have also purchased a muffle furnace. We already have UV spectrometer. So all these techniques, once are established in the lab, we will be able to motivate the students, and that is the present scenario why we have organized this seminar. And the future obviously is going to be great, and I request all my senior colleagues in the form of Professor Vinay Gupta, Professor Vinay Kumar, and Professor Bijoy to extend a helping hand in establishing this lab so that we can motivate the students, and we can go a long way in not only developing a scientific temper, but the young teachers, young faculty that we have. Recently, we have included, inducted young dynamic faculty members who are specially trained in experimental physics. We already had few dynamic people with us, but apart from that, the young induction once again is going to work in that direction. So I am extremely grateful to our principal, young dynamic principal that we have, who has always extended a helping hand to any idea that we move to him, and Dr. I.K. Singh for extending any financial or any technical expertise that he can provide to us. And we already have with us the young dynamic faculty of physics department, of which I am also a part of it. May not be that young, but still I take that as a compliment to me. I once again give the screen to Deepti for moving ahead to the next program.
Thank you so much, sir. Thank you, sir, for such an enlightening words for the two-day national seminar. Now I request our esteemed, dynamic, active, our own principal, sir, Dr. Rajiv Agarwal, to kindly formally welcome our August gathering. Principal, sir.
Thank you, Dr. Deepti. Very good morning, namaskar to all dear friends, students who are here from all around the globe, all around the country. Dr. Tyagi has snatched almost all the content of my speech that I prepared. So I don't repeat all those things. It gives me great privilege, honor, and happiness to welcome all of you to this 2 days national seminar on recent trends on contemporary physics, which is organized by Department of Physics, Deshbandhu College, in collaboration with our IQAC, under the aegis of DBT Star College scheme. I would further like to extend my special welcome to our esteemed speaker for today, Professor Vinay Gupta, Department of Physics and Astrophysics, University of Delhi. I know him for almost more than 27 years. He is a complete, what I can say, scholar, researcher. He is one of the best physicists in India. Presently, we are having empty number of publications. Probably he is one of the physicists having largest number of citations in India. More about, he is a gentleman, always ready to help, particularly me as well as our college, Deshbandhu College. As Dr. Tyagi said, he is our governing body member as well. In the past as well, he was always ready to help us. Our next speaker, whose sessions will be having tomorrow, Professor Vinay Kumar. Although I don't know Professor Vinay Kumar for very long, but very recently I interacted with him regarding the cases of promotion and interacted some of his students as well. He is also in the same category, having empty number of publications, large number of students he has supervised. My apologies. And one more speaker for today, Professor Vijay Kumar, Special Center for Nanosciences, Jawaharlal Nehru University. Probably Professor Vinay Gupta and Professor Vijay, they are the experts in the nanosciences and nanomaterials. I hope that we'll have great sessions with all our three esteemed speakers. I would also like to express my gratitude to all the participants on behalf of my institute, Deshbandhu College, University of Delhi. This seminar will be mainly focused on outstanding material for energy harvesting and hazardous gas monitoring sensors. Recent crystalline structures which will be beneficial for industry and society. Also GMR-based biosensors which can be used for biomedical applications like direction of proteins, DNA, as well as mapping of cardiovascular and brain signals. Friends, the Department of Physics of our Deshbandhu College is also actively engaged in trending research areas like condensed matter physics, nuclear and nuclear particle physics, quantum teleportation, energy harvesting applications, and liquid crystals. The department under the DBT Star College is involved in innovative research favorable for our undergraduate students. In the end, I would like to congratulate our Department of Physics, mainly in the convenership of Professor UP Tyagi and all the members of the physics department, our IQAC coordinator, Dr. Aditya Saxena, our DBT Star College scheme coordinator, Dr. Indra Kant, for organizing this webinar. There are two observations and suggestions in the end. That number one, we should mobilize our students more. I'm seeing that very less number of participations right now. So we should mobilize our students in the college as well to attend this program. Secondly, we must adhere the timeline and the program schedule for any webinar and the seminar. Thank you very much. Over to you, Deepti.
Thank you, sir. Thank you, sir, for such a warm welcome. And your suggestions will be definitely carried out, and we'll see towards more participation of the participants. So now I request Professor Vinay Kumar, Professor, Department of Physics and Astrophysics, University of Delhi, to share his valuable words about this seminar with our August gathering. Professor Vinay Kumar, sir.
Thank you for organizing this conference. Thank you, Principal Sir, Dr. Uday Tyagi Sir, Professor Vinay Gupta, my very close friend. I am very happy that your college is organizing a good conference on a good topic. And I just hope that it will be very beneficial for the student and the young faculty as well. Thank you very much. I have done. And congratulations to all organizers. Thank you.
Thank you, sir. Thank you, sir, for your motivating words. T.S. Eliot has rightly said, only those who risk going too far can possibly find out how far one can go. I request Dr. Indra Kant Singh, sir, Coordinator, DBT Star College Scheme, to address the gathering, Dr. Indrakant Singh, sir.
Thank you, Dr. Deepti. Thank you so much. And again, I would like to welcome our esteemed speakers of the day, chief guest of the day, our principal, sir, and senior colleagues from physics department, and dear friends and students. Thank you so much, first of all, to organize such a apt topic of the day, that is recent trends in contemporary physics. Being an DBT Star College Scheme coordinator, it is always a great privilege and happiness for me if any of the program organized by our esteemed colleague from any of the 5 departments who has got this scheme in 2019. And if I talk about, I'm not a physics person, but yes, the target or objective of this scheme is to design a work, program, course, workshop in a manner that almost all the science departments should involve and get benefited, to motivate our young minds to work in interdisciplinary science, which ultimately going to benefit to the human welfare. What I understood by the simple topic is that this national seminar focuses on exploring the recent development in the physics. The aim of this seminar is to provide a forum to innovate academicians and researchers for dissemination of contemporary research and ideas on wide range of issues related to physics, and yes, ultimately to our human welfare. So I must again thank our organizing team, and especially the young colleagues of physics department. They are very, what we call intelligent, what we call the well-versed of the new techniques. And yes, this is not the DBT only, DBT Star College scheme. I will keep doing same kind of resource generation, because I'm not an expert in physics, but whatever way I can collaborate with these young teams or the Department of Physics to add on biological component of any of your venture. And I must mention at this forum that Professor Binay Gupta, sir, whenever I have requested him to please come and deliver your talk or, motivate our young minds, not from our college only. So every year we are organizing DST Inspired, and where we used to select 200 students of the 1% of topper from CBSE. And yes, in physics, Professor Binay Gupta, sir, always obliged us to spend his valuable time and interaction, not only alone him, with his complete team, and demonstrate such wonderful experiments and tools and techniques to the young minds. They always remember, and always whenever I send the invitation for the program, they always ask, sir, wo wale sir aa rahe hain ki nahi aa rahe hain, So that is the impact. And he always encouraged me as well to indicate if you need any kind of help, any kind of collaboration. So same I'm expecting for other esteemed, the professors from the physics department whom I never met. But yes, this is the right forum that I will going to interact with him, Professor Binay Kumar, sir. And I hope I have met before Professor Bijoy Kumar from GNU. I think he also came a few years, last 2 years before probably, if I'm correct. So thank you so much, our esteemed, the professors and the speakers of the day. But just I'll take one more sentence here. For anything we have to dream big. And when you have a big dream, and if I just quote this dream, convert it into a simple journey, I could say, in a form of physics, that for any dream, if you convert it to a journey, and if it is a the flight journey, you could say the 3 things is very important to being a good captain. And for captain is important is, first point is takeoff. So we got a great takeoff from our great captain, Dr. Rajiv Agrawal. And most important is, once you are on journey on air, very, very important and crucial step to reach to the right destination. And those destination is always navigated by what we call the traffic control. So that traffic control, I could say, our experts from different fields, like Professor Vinay Gupta, Professor Vijay Kumar, or Bijoy sir. So that is very, very important. And yes, so finally, we have to land at the right destination. So takeoff, landing, and right navigation is very, very important. We are just, a simple, what we call the yatrigan hai hum to. Hum saath chal rahe hain. We are giving our own all efforts. And yes, we have great hope from our complete team of physics department that we will reach to the right destination. And in that journey, there is one small stop is we have established nano physics lab. And besides that, we have already established with all the 5 science departments in collaboration with them and sponsored by DBT, and the great support from our own management, college management, our principal, that we have established I4 Center, that is Interdisciplinary Science Innovation Idea Center, and that will going to cater not only to the students, but our young faculty who wanted to, plan or execute their innovative ideas. Thank you so much, Dr. Dipti, for giving me chance and express my views. And I wish good luck and great success for this national seminar. Thank you. Over to you, Dipti.
Thank you, sir. Thank you for your motivating words. And we shall definitely work on the collaboration of the interdisciplinary research projects that is proposed by under the DBT Star College projects. So I request Dr. Aditya Saxena, Coordinator IQAC, to address the August gathering. Over to you, Aditya.
Aditya sir, you are muted.
Aditya sir, kindly unmute yourself.
Yeah. Am I audible now?
Yes, sir.
Was I audible earlier or no?
No, sir, you were not
Not even
audible.
audible.
So thank you, Deepti. And on behalf of the Internal Quality Assurance Cell, Deshbandhu College, I, Dr. Aditya Saxena, extend a very warm welcome to all the respected dignitaries and participants of this 2-day national seminar on recent trends in contemporary physics, which is being jointly organized by the Department of Physics and the DBT Star College Scheme Deshbandhu College under the aegis of the IQAC. I especially extend a very warm welcome to our distinguished speakers for the inaugural sessions, both today and tomorrow. Professor Vinay Gupta, Dean Faculty of Technology from the Department of Physics and Astrophysics, University of Delhi, and Professor Vinay Kumar, Department of Physics and Astrophysics, University of Delhi. Sir, it is indeed an honor to have both of you over here amongst us. I would like to take this opportunity to give a brief introduction to the tremendous progress that our college has made and the significant activities that we have planned. And in undertaking all of this, all of this has been actually possible under the dynamic leadership of our respected principal, Dr. Rajiv Aggarwal. And the college has achieved many milestones under his leadership. The most notable amongst them being that the college secured 96th All India rank in the colleges category in the National Institution Ranking Framework 2020. We have been awarded the DBT Star College Scheme in 2019, which has given tremendous impetus to our research profile. The faculty of our college from all the disciplines has published more than 150 research publications and many books in the last 1 year. Despite the conditions of the pandemic, we have been very active and have organized 3 international events, 77 national events, 3 faculty development programs, and several outreach programs for the society and the students under the banner of NCC and NSS. Our college has taken significant strides in the field of energy conservation and nature conservation and is poised to be declared the Green College. We are also going in for a green audit of our campus. Our campus has adopted green building norms, rainwater harvesting, and we have a composting pit, a botanical garden, and are developing a green belt with amphitheater, bonsai garden, and a multi-purpose court. Our library has been awarded the best library in Delhi University by an independent jury. Our department has also emerged as a significant player in the area of physics education and research. And we have, in the last 2 years, established 2 research-level labs in nanomaterials and optics and spectroscopy. So with this brief introduction about the college, I would now request Dr. Deepti Goyal to continue the proceedings of the day. Thank you so much, and over to you, Deepti.
Thank you, sir. Thank you for your motivational words and telling about the IQAC, that work has been done in the college. So thank you, sir, once again. So I request Dr. Ajay Pratap Singh Gehlot, Department Coordinator, Physics, DBT Star College Scheme, to speak few words. Over to you, Ajay, sir.
धन्यवाद दीप्ति, मेरी आवाज आ रही है?
हाँ जी सर, हाँ जी।
आदरणीय प्राचार्य महोदय डॉक्टर राजीव अग्रवाल, आदरणीय प्रोफेसर विनय गुप्ता सर, आदरणीय प्रोफेसर विनय कुमार सर, आदरणीय प्रोफेसर विजय कुमार सर, डीबीटी देशबंधु कॉलेज फिजिक्स डिपार्टमेंट की ओर से मैं आप सभी महानुभावों का आज के इस सेमिनार में स्वागत करता हूं और आपसे विनम्र प्रार्थना है कि आपका जो मार्गदर्शन और समय हमें पिछले गत कई वर्षों से मिल रहा है वो आगे भी मिलता रहे। मेरे से पूर्व के वक्ताओं ने कॉलेज के विषय में कई जानकारी दे दी है, तो भी संक्षिप्त में अगर डिपार्टमेंट की बात की जाए तो जैसा कि हमारे इंचार्ज साहब ने कहा कि हमें विनय सर ने कई बार संकेत किया कि किसी प्रकार की तकनीकी या टेक्निकल जो भी नैनो लैब से रिलेटेड समस्या या कोई भी सहायता है वो दे सकते हैं, उन्होंने दी भी। हम सब ने ध्यान है कि हमें 2019 में जो दिल्ली विश्वविद्यालय में प्रथम अपना सेमिनार कॉन्फ्रेंस किया था उसमें किस प्रकार से आप सभी महानुभावों ने अपनी भरपूर सहायता हमें दी। उसी प्रकार डीबीटी स्टार कॉलेज प्रोजेक्ट की विभिन्न प्रकार की जो प्रक्रिया गत वर्ष 2019 में और 20 में भी हुई, उसमें भी आपकी हमें कई प्रकार से सहायता मिली, जिसमें उल्लेखनीय 2 दिवसीय हमारा जो सेमिनार रहा उसमें और फील्ड ट्रिप उसमें भी आपकी सहायता मिली। इसी प्रकार डिपार्टमेंट में जैसे अभी त्यागी साहब ने बताया कि कई प्रकार के हमने संसाधन और इक्विपमेंट्स खरीदे हैं, उसमें भी आपके द्वारा हमें समय समय पर मार्गदर्शन मिला। अभी वर्तमान में डिपार्टमेंट में 8 प्रोजेक्ट चल रहे हैं जिसमें हमारे जो सहयोगी शिक्षक हैं वो विद्यार्थियों को अपना मार्गदर्शन दे रहे हैं। तो संक्षिप्त में इतनी ही जानकारी आज के लिए पर्याप्त है। तो आगे की कार्यवाही के लिए मैं दीप्ति को पुनः आमंत्रण करता हूं।
धन्यवाद अजय सर, धन्यवाद। So now I request Dr. Pankaj Singh to formally introduce Professor Vinay Gupta, Professor, Department of Physics and Astrophysics, University of Delhi. Dr. Pankaj Singh.
Thank you, Deepti, and good morning to all of you. It's my great pleasure that department provide me the opportunity to introduce such a eminent scientist and a great teacher, Professor Vinay Gupta sir. Professor Vinay Gupta is serving at the Department of Physics and Astrophysics, University of Delhi as a professor since 2004. His current research area include semiconductor and surface acoustic wave, sensor for gas, chemical, radiation, biomolecules, photometric biosensor, surface plasmonic resonance techniques and dielectric studies and sensing application, microfluids, nanostructure materials, piezoelectric and multiferrous thin film ceramics for energy harvesting application, pressure sensor, RF and microwave resonator, photonic device, non-linear optical studies, SWA device, MEMS transducer and micro heaters. He has developed electronics material and device laboratory, which is well equipped with high-end instrument like laser, MBE, PLD, sputtering and device fabrication technique to name of a few. His research group is internationally recognized, working in the area of processing and development of multifunction electronics materials. He is engaged towards the development development of integrated devices have strategic as well as ceramic commercial application. His research group has successfully integrated piezoelectric zinc oxide thin film with MEMS structure fabrication by Siri India of acoustic sensor as per specification desired by the Indian Space and Organization. These acoustic sensor has been installed in the PSLV flight of ISRO for C9 onwards. He has published more than 445 research paper in high impact factor SCI journal. He has been granted 1 US and 3 Indian patents, along with one successful technology transfer of indigenous developed tabletop SCR system, which is being used in a various academic and research institutes. He is an active member of various reputed research societies like IEEE, MRSI, EMSI, etc. At present, he has projected grant of more than 4 crore rupees. He has received MRSI medal 2012 presented by the Material Research Society of India, and also recently received Distinguished Teachers Award by the University of Delhi. 2 days ago, one more feather is added on his cap when Stanford rank of world best scientist was announced, in which he ranked amongst the top 2% of scientists. So now finally, on the behalf of the physics department, I welcome Professor Vinay Gupta, sir. Thank you, Deepti.
Thank you, sir. So now I request our honorable speaker, Professor Vinay Gupta, sir, to kindly come and chair his session and speak about his talk. Professor Vinay Gupta, sir.
Thank you, Deepti. Am I audible?
Yes, sir.
Yeah, first of all, I'm thankful to the principal, sir, and the organizing committee for giving me the opportunity, and also Pankaj for such elaborated introduction. Only one correction is there, that I have not received any Best Teacher Award from the university. So that's the only correction there. So today talks is on 2D, two-dimensional MOS2 layer, outstanding material for environmental monitoring and energy harvesting. So if you see the technological progress around the world, 19th century was driven by the steam engine. And because of that, it was possible for the people to migrate across the cities. Then 20th centuries were dominated by electrification and combustion engine, which promote the global trade. And 21st century is the era of information technology, semiconductor technology. So now we are in the globalization and artificial intelligence world. If you see, and you have the idea of electronic chips. So there's a well-known law, which is known as the Moore's law, and according to which the technological node size is going to shrink almost half every year. You can see here, every decade. And you can see now we are around at 20 nanometer or 10 nanometer where 3D geometries are there. People are using, and they have shifted from planar geometry to the 3D geometry. And still we are greedy and we want to miniaturize further. We want to reduce the node, that means the gate length further. And for that, we are almost at the state of art of transistors, and it is difficult to go beyond this node using the conventional silicon or 3-5 semiconductor. So then the question is, what is the solution and how to miniaturize achieved with further advancement? For that purpose, scientists are looking for new materials so that this conventional silicon or 3-5 compound can be replaced for transistor applications and can go ahead. So in that case, the 2D material, the two-dimensional materials is a key solution, which are totally different from the conventional, the silicon and gallium nitride or 3-5 compound semiconductors. In this material, individual layers of covalently bonded atoms and molecules are held together by van der Waals forces, such that layer by layer can be exfoliated. So this is a very crucial. You can see here, this is a single layer. In the single layer, atoms are bonded by the covalent bonds. And if you see the adjacent layer, there is no covalent bond in the adjacent layer. They are interacted only with the weak van der Waals forces. And then in second layer itself, again, there's a covalent bond. So this continues so that you can remove or you can add layer by layer. So that is the advantage in the case of 2D material. As far as 3D materials are concerned, like silicon and 3,5 compounds, which are conventional semiconductor material, in that case, in Z direction, the Z direction, also covalent bond exists. Whereas in this case, only the van der Waals forces exist. So that's the basic difference between the conventional 3-dimensional material and the 2-dimensional material. Also, if you want to make the nanomaterials from 3D materials and you want to reduce the thickness of 3D material so that a monolayer or bilayers can be achieved, that is possible, but still there is, because of the covalent bond in the Z direction, there is the possibility of existing of dazzling bond, which is not present in the case of 2D materials. That's the advantage of 2D material. So the key features of 2D materials are that they have the high carrier mobility, even at sub-nanometer thickness, which is not possible in the case of conventional material. Stacking is possible in the desirable manner. You can make the multi-layers by using putting layer by layer on above each other. And each layer has a very good mechanical flexibility so that you can use for flexible electronics in future applications. So if you see the 2-dimensional materials, they can be metal, they can be semiconductor, and they can be insulator, oxide materials. So the well-known families is graphene, the carbon-based graphene, graphene oxides, hexagonal boron nitrides, or the chalcogenides group, which are semiconductors or oxide materials. All these are 2D materials in which in the Z direction, there is no covalent bond. The covalent bond exists only in X and Y directions in the material. So transition metal chalcogenides are the most important classification of material if you are working with the transistors or you want to make some semiconductor devices. So these 2D materials are semiconductors in nature. What is the advantage of 2D transition metal semiconductors? You see here, because I mentioned you that about the carrier mobility. High carrier mobility even at some nanometer thickness. So you can see here, if we reduce the thickness of the material, the blue is the conventional silicon material. And if you're reducing the thickness of silicon, the carrier mobility is decreasing significantly. And if you're going below the 2 nanometer, you can see it almost comes to the 0 or very small, around 5 or 3 centimeters square per volts per second. Whereas in the case of MOS2, if your thickness is small, even then your carrier mobility even up to 0.5 nanometer is around 10 centimeter per volt per centimeter. So that's the advantage, that significant or sufficient mobility present even for smaller thickness of 2D materials. You can see here, for example, the FET, the FET configuration, the gate oxide and 2D material. So there is a quantum well, and you can confine the charge carriers very well because this a layer by layer deposition is there, and you can make the monolayer or bilayer. Whereas in the case of conventional 3D material, the gate oxides, and this is 3D material, in that case, the quantum value is not well defined because the thickness is not well defined and your wave function is like this. So in this case, what happened? The one advantage of 2D material is that you can preserve the mobility. Mobility is significant, clear. Secondly, dazzling bond. In the case of 2D material, there is no dazzling bond because layer by layer interaction is by van der Waals interactions, whereas in 3D material, their interaction layer by layer is covalent bond. In Z direction also covalent bond is there. So if you are going to make the slice a small thickness, it will lead to the dazzling bond in the conventional semiconductor. So as far as controls are concerned, the better electrostatic control is possible because of well-defined quantum well here, and heterostructure can be formed of high quality with high quality interface. Band gap is tunable. You can tune the band gap in 2D material by changing their thickness from monolayer to the 10 layer or more. They are flexible and very good for flexible nanoelectronics. What are the challenges for two-dimensional transition metal chalcogenides? The challenges are that these materials are very difficult to grow over the large area because they are just by exfoliation. You can remove the material. When you're removing the material, the removal of continuous material is very difficult. So large area continuous growth is a big challenge. Then controllability in the growth or homogeneity in the growth is a critical issue. After that, the ohmic contact or the Schottky contact, the selection of metal contact with 2D materials is another challenge, and charge carrier scattering because of a lot of defects in the material itself is the challenge, and they are sensitive to the dielectric ambient environment. So out of these 2D materials, which we have listed, the number of 2D materials are there. Which material is the promising? MOS2 seems to be the most promising material, but not limited to the MOS2 also. There are other materials also. But in my view, MOS2 seems to be the most promising material because they are naturally available. They are stable in environment and can tune the band gap from 1.2 electron volt to 1.8 electron volt depending upon the thickness, the monolayer to the 10 layer of the system. This is a crystal of the MOS2, and you can thinning down and you can make the monolayer. This is the monolayer of MOS2 where your molybdenum is embedded between the sulfur layer and sulfur layer. So MOS and S, MOS2 is there, and applications are enormous from transistors, photodetector, heterostructure, photovoltaic sensing platform, batteries, and nanogenerator, etc. So what is MOS2? If you go to the one layer, single layer, if the structure is basically the hexagonal. Unit cell is hexagonal here, and molybdenum is embedded between two sulfur one, and this becomes one layer. So this is the one layer of MOS2 where MO is embedded between the sulfur, and the thickness of one monolayer is around 6.5 angstrom, 0.65 nanometer. Clear? And each layer, as we discussed, have the covalent bonding in hexagonal form, and each layer you can say has the weak van der Waals forces in this case. So this then, with increasing the number of layers, it becomes the bulk structure. And lattice parameters are given here, just 3 angstrom and 12 angstroms are here. How to grow this material? To grow this material, option is that either you can do the exfoliation. Exfoliation means you can remove the material one by one by using the Scotch tape. Or you can use chemical vapor deposition, or the new technique is, you can say, is pulse laser deposition. So in my talk, I will more focus on pulse laser deposition. Why? Because the PLD will give the stoichiometric and continuous growth of deposition. It needs the high vacuum ambience, so the possibility of defects in the system is very, very less. And excellent control is there on the thickness of this material. You can make by changing the number of pulses. You can make the monolayer, bilayer, tri-layer, or you can control the thickness very precisely. So if you can control the thickness, the interface also you can make very sharp, very efficient. This is a very safe, clean, and highly efficient technology. Manageable growth kinetics is there. So if you see the pulse laser deposition technique, you need a high vacuum chamber in which you have to put some target of the material, like in this case, the MOS2 disk is needed. Then at 45 degree, you have to inject the high power pulse laser beam. And when the interaction is there, there is a plume which coming out, ejecting out the materials, and you can deposit the material over the substrate. The substrate can be rotated to make the uniform coating, and also you can provide the heating so that a proper nucleating center is there in the system. So this is a just basic idea about pulse laser deposition system. You can see here how the plumes looks like in actual. And this is the pulse laser deposition technique which is available in our laboratory here. And to make this material, you have to play with number of parameters. That's the advantage of pulse laser deposition, that you can play with different parameters. You can change the ambient because there is no oxygen. So I'm using the non-reactive inert gas nitrogen as in the chamber. And then substrate temperature can be varied from 600 to 800. Even you can change, it's up to your choice. But I'm changing from 600 to 800. Laser energy is there, base pressure. Better the vacuum, less the defects are there in the systems. Then the processing or growth pressure, 1 millitorr by using the nitrogen ambient. Target to substrate distance we can vary, but I have fixed to 6 centimeter depending upon our experience in the laboratory. And the number of laser pulses we can change from 50 to 2000. 50 is for monolayer and 2000 is for bulk sample. And since we need a ceramic target here to interact with the laser to create the plume, so we have to mix the powder, we have to press it by hydraulic press and sinter it to make a solid target. And the target, you can see here, is placed in the inert atmosphere, and then the sintering so that the densification is there. And this is the XRD, you can say, of the target, just to ensure that the target is pure, there is no other impurity is present. And this is well with the literature, indexing with the literature, which confirm that target is MOS2. So this target has been used in the system with these processing conditions. Parameter has been changed. Mainly the substrate temperature has been changed so that we can grow a good quality MOS2 layer. Just see the example here. We have changed the temperature, and this is a Raman spectroscopy of the thin film which has been deposited. Two modes, E12G and A12G, which is well-defined modes of MOS2 is there in the literature, has been obtained. And you can see the literature. The literature, these two modes are obtained at 383 and 408. And these modes are quite close for the film, which deposited at 700 and 800 degrees centigrade. So 600 we have discarded. So we focus for future work on 700 and 800 degree temperature. And also you can see the full width of maxima, which shows that these peaks are sharp, crystalline crystallites, or you can see the grains are larger. That means the better crystallinity of the MOS2 is there at 700 and 800 degrees Celsius. So we succeeded in making the MOS2 by using the pulse laser deposition techniques, which is very difficult to grow the large area deposition. In this case, we use a substrate temperature of 1 centimeter by 1 centimeter. And the deposition is over the entire 1 centimeter by 1 centimeter. Then we change the number of pulses, as we mentioned, from 50 pulse onwards. And you can see here, with 50 pulse, we got the monolayer, 70 pulse, we got the bilayer of MOS2, 100 pulses, we got the tri-layer, and 150 pulse, we got the quad layer. So that means that we can control, we can tune the number of pulses, and by tuning the number of pulses, we can obtain the monolayer, bilayer, tri-layer, etc., the different layers of these materials at both the temperatures, 700 degree temperature and 800 degrees Celsius temperature. This is an atomic force microscope photograph, and you can see here we have just shown the uniformity and uniform distribution of 3 consecutive grains, which suggests that the growth is very homogeneous, which is very difficult to obtain in the extrapolation. So very homogeneous growths are obtained at 700 and 800 degrees Celsius. And you can see the thickness here when the bottom layer was SiO2. Over the SiO2, MOS2 has been grown, and you got a thickness of 0.72 nanometer. And we have just shown you in the beginning, in literature, the thickness of monolayer is around 0.65 or 0.7 nanometer. So that means we clearly obtained the monolayer, and the thickness is obtained from the atomic force microscopy, which shows a monolayer growth with uniform distribution of grains by using pulse laser deposition. We also perform just to see the compositional analysis of the MOS2, whether stoichiometry or composition has been maintained or not. So this is XPS of the molybdenum and sulfur S2, and this is the XPS of sulfur 2P, this one. And by composition, what we find out that molybdenum has 18.48 and sulfur has 35.62. That means the ratio of sulfur to molybdenum is around 2. So that clearly shows that MOS2 has been formed. And further, there is no peak at around 236 electron volt, which represents the formation of oxide of the molybdenum, which clearly indicates that there is no trace of oxygen in the XPS in the growth of MOS2, and pure MOS2 has been obtained by using the pulse laser deposition technique. So these are some read analysis. I'm just showing you just because this is a seminar on contemporary physics. So I am just exposing you with advanced technology. So these are the tools which read, which has been installed in our system, pulse laser deposition systems, which indicates in situ growth of the MOS2. So this is the read pattern at 700 degrees Celsius with different number of laser pulses, 50, 70, 150. And these are the read patterns at 800 degrees Celsius. And this is on sapphire substrate, and which clearly shows that patterns are very streaky, very sharp, which clearly shows that MOS2 monolayer has been grown at 800 degrees Celsius successfully, and the crystallinity is very, very good as compared to those systems which has been obtained by acceleration. In acceleration, you can't perform the read analysis. Read analysis can be performed only in situ when you are depositing the material atom by atom or molecule by molecule. These are photoluminescence studies just to ensure whether the MOS2 is there or not. This is the read PL spectra of single layer, monolayer MOS2, and then bilayer, trilayer, and quad layer. And in this case, you can see here the peak is sharp for A, and then the peak is sharp for B. That clearly shows that band gap of the material is also tunable here, and defects in this, because two peaks are well-defined, exciton peaks are there, which clearly indicates that the defects are minimal in the growth of MOS2 by PLD technique. Again, we use very high resolution transmission electron microscope just to see what is the thickness of our ground film, because we have checked with the AFM. Now we tried with the HRTM, which is more precise technique to identify the thickness of the layer. In this case, the substrate was silicon dioxide, and on the bottom side, the substrate was sapphire. And you can see in both the cases, we got the thickness of around 1.94 nanometer, which is corresponding to tri-layer. So these are the HRTM for 100 shots of the laser pulses, which leads to the tri-layer deposition of MOS2. So if you see 0.65 multiplied by 3 roughly comes out to be 1.9. So that clearly shows that these are the tri-layer of MOS2 has been successfully made, and interface is very, very sharp. Interface is very, very sharp, which clearly shows the advantage of pulse laser deposition over other technique in making the very good interface and very good quality MOS2. Now, I will go on to the application part. Since MOS2 has been grown, monolayer, bilayer, tri-layer, etc. has been made. So we try to make the photo detector. Why can't we try these layers to make the MOS2 here? So we put the bilayer, monolayer, and all different thickness of MOS2 here. And 2 electrodes are put of ITO, which is transparent and not going to obstacle the light. And then applied some bias here, around 2 volt. And then we studied the photo response characteristics of this. And these are the deposition parameters, which we optimized. 800 degree temperature we fixed. And then number of laser pulses we changed from 50 to 400 to make the layers 1 layer of MOS2, 2 layer of MOS2, 3 layer of MOS2, and 10 layer of MOS2. And you can see, because I mentioned you in the beginning, that contact electrode is very crucial. So that's why we try gold, silver, platinum, titanium, and ITO as the electrode. And in this case, if you see the dark current for the ITO is this, and photocurrent for ITO is this orange one, and very large change in the current is observed with the ITO. So ITO seems to be the best electrode as far as UV photodetector application is concerned. As far as platinum titanium is concerned, this is the dark current and this is the photocurrent, which is very less. And similarly, this is a dark current for gold and silver, and this is the photocurrent for gold, silver. So I will say out of these three, the best electrode comes out, or the best photo response comes out for ITO electrode. So ITO MS2 interface gives the maximum photo current, and the optical response of the system also depends upon the thickness. So we try to change the thickness of the MOS2 in the same configuration from 1 layer, 2 layer, 3 layer, up to the 10 layer. And you can see this is a dark current. And with 10 layer, this is the photo response. 6 layer, this is the photo response. So with the decrease in the thickness of this MOS2, the photo current starts increasing. Or you can say the responsivity of the photo response was found to decrease with the increase in number layer, which gives the advantage of increase in surface to volume ratio, or you can say the number of layer is less, better the photo response, better the responsivity, better the photo current. So the UV detector is good if your layer is small. So mono layer, you can say, is the preferred one to make the photo detector. Single layer MOS2 based device gives the maximum responsivity in the system. We applied different lights, different wavelength, and we found that the lower wavelength, higher energy corresponds to gives the better responsivity as compared to the higher wavelength or lower energy. Also, the incident power dependency, you can say, is almost a linear response is obtained in the current with increase in the intensity of the UV light, which clearly shows that the contribution from the trap, because this is a more physics-based concept, the trap always participate in the photocurrent, but if response is linear, that means contribution from the trap centers where charges are trapped are going to be minimal, and the major contribution is from the band conduction in this case. Repeatability study has been done for the photo response, and you can see here with different bias, 0.5 volt we applied, then 1 volt we applied, 1.5 volt we applied, and 2 volt we applied. In all the cases, the baseline remains the same. There is no drifting in the current, and repeatability is there. Light off, when light on, the photo current is more, and when light switch off, again it comes back to the original position. And this repeatability, then you can use the same photo detector for number of times. So in this case, we have shown for 5 cycles, but we can continue up to 20 cycles of 100 cycles. There is no change, you can say, in the no drift in the base current is obtained. And all these are the parameters which is obtained at different bias voltage, And you can see here the best performance which we obtained is at 2 volt in the system. So this is the literature. From literature we have compared, and you can see our value of responsivity, detectivity, on-off ratio are found to be much higher as compared to the values reported by other peoples by using other techniques, mostly by acceleration or chemical vapor deposition techniques. So you can see the advantage of pulse laser deposition or other systems. So in this case, just for comparison, we have put some other materials also so that you can compare the MOS2 with heterostructures of other materials, and you can compare and you can see the results. Then we try to make the heterostructures of the 2D material. Is it possible or not? Because 2D material, the growth itself is challenge, but we attempted, can we make the heterostructures of 2D material? And in always, to make the heterostructures of 2D material, there's always a problem of contamination, interface problem, choice of precursors and proper transfer from one location to the other location, lattice mismatch between the 2 layer, controlled chemical reactions. There should not be any interdiffusion between the 2 layer. And because of interdiffusion, there's a possibility of formation of byproducts. And then kinetic for layer control synthesis is very crucial. So in this case, we try to use again the pulse laser deposition technique so that stable 2D layer of different materials can be stacked together, because by PLD, as we mentioned earlier, we can grow the stoichiometric material and can be grow and can be controlled in controlled manner, can be put one over the another. So resulting artificial 2D structure provide access to new properties, including enhanced electronic and optoelectronic properties, and applications is beyond their counterpart. That means if we are using two different compounds, then the composite material or the heterostructure will give the better results as compared to the individual results. This 2D layer can be integrated into a monolayer if we are integrating in the lateral two-dimensional heterostructure, or we can make the multiple stacks if we are going to stack one over the above in the Z direction. So, but the problem is again that scalable growth and particular stacking order between different layers and material remain an issue. Those are the challenges. So we use another 2D material, WS2, and we want to make the heterostructure of MOS2 with WS2. So to grow the WS2, we use a nitrogen ambient and similar processing conditions as we discussed in the previous case we used. The only difference is that the number of layers which are optimized for monolayer, bilayer, tri-layer, and bulk are going to be more, because in the previous case, in the MOS2, we used only 50 shots. In this case, is 250 shots and 300 shots. So short number of shots required to grow WS2 is more. I can quickly go ahead now very fast, because all these are the just, you can say, the characterization tools, which I already discussed with you people in the at a time of MOS2. So in this case, you can just compare. So just see here, this is a monolayer, 2-layer, 3-layer, and 5 layers systems are there of WS2. And these are the XPS spectra, which clearly shows that only 2 peaks are there, and there is no impurity is present in the WS2 systems. And by using this, we try to make here the heterostructure of WS2 and MOS2. So WS2 is here like this, and MOS2 is here in this case. And both these heterostructures we put over the ITO here, and then the top electrodes we use the gold and silver. So this is the, you can see the Raman spectroscopy of this heterostructure. So where we got the peak of WS2 and MOS2 both, and these are the XPS, you can say the spectra, the PL spectra of one monolayer of MOS2 and one monolayer of WS2, and this is the PL spectra of composite. You can see the heterostructure having the peak of both, and then the photocurrents we obtained for different wavelengths for this heterostructure, and I will give you detail in the later slides. You can see here, as a function of wavelength, 405 nanometer gives the best responsivity as well as the detectivity. Both are found to be very, very high at lower lambda when applied bias is 2. And these are the response for heterostructure, not the individual layer. And you can see here also the repeatability and the response, and response was found to be much, much higher. The dark current is same in all the cases at all wavelengths, but photocurrent you can see is maximum obtained at 405. Response time and recovery time, you can see 40 nanometer and 50 nanometer, which has been obtained. And this is a power dependency or intensity dependency of this. And this is a comparison with the literature. And you can say the comparison also, the response, the responsivity and detectivity which we found is much, much better as compared to the other heterostructures of 2D material, which is reported in the literature by using the other techniques. So in this one, the response is much, much better. So I will go with another applications, the transistor which we try to make with the MOS2, because ultimate goal is that we should go with the transistor with smaller nodes. If monolayer, with monolayer we can make the FET, then scalability issue can be resolved. And the Moore's law is, you can say we can go beyond the Moore's law more and more. So in this case, we use the silicon as the gate, which is degenerate semiconductor, having very good conductivity. You can see here, resistivity is very, very low. And then silicon dioxide as the passivation layer. And on top of that, we put the MOS2 as the channel. And here we change the thickness of this channel, the monolayer, bilayer, tri-layer, and then source and drain. And the separation between source and drain is just 20 micrometer. And these are the masks using which these transistors has been fabricated in the laboratory. And thickness of the silicon dioxide, the dielectric, we try to change first from 60 nanometer to 90 nanometer and 120 nanometer. And then we study the output and transfer characteristics. So these are the transfer characteristics, and these are the output characteristics by using silicon dioxide 60 nanometer, 90 nanometer, and 120 nanometer. And you can say well-defined transistor characteristics were obtained as in the case of FET. Clear? And threshold voltage we can check here. These are the semi-log graph of, you can say, the transfer characteristics same as we've shown in the previous one. These are the linear one, and these are the semi-log graph, and these are the parameters which has been obtained from the transistor parameters which has been obtained. And you can see the mobility here is around 20. On-off ratio, the switching transistor, you can say we can make on-off ratio is 10 to the power 5, and threshold voltage is minus 2.5. So 90 nanometer thickness of silicon dioxide seems to be the optimum to make these devices. So then we tried, why can't we make the silicon nitride instead of silicon dioxide? So same experiment was repeated with silicon nitride having 60 nanometer, 90 nanometer, 120 nanometer, and transfer characteristics and output characteristics are there. And these are the semi-log graph, and these are the parameters with silicon nitride, which gives the better results even as compared to the silicon dioxide. So silicon nitride seems to be the more passivity, good passivation layer in transistor, and 90 nanometer thickness was found to be the optimum in this case. Yeah, and then we try to change the thickness of this MOS2 monolayer, because we fixed silicon nitride, and the thickness of silicon nitride we fixed 90 nanometer, and we changed the monolayer of MOS2 from the thickness of MOS2 from 3, 6, 8, 10, and 14, and you can see the characteristics of transfer characteristics here, and the mobility you can see we found maximum at a particular thickness of MOS2, around 10 layer of MOS2, and after that and before that the value of mobility is less. There's a specific reason for that. I'm not going into the technical detail why this thickness is optimum here, because that needs more discussion. But you understood that the thickness of this MOS2 is very crucial in optimizing this. Same transistor we try to use for gas sensing application. The only thing is that we change slightly the configuration, that instead of the circular electrode on top, we put the interdigital electrode here, like in this form IDT. Here, and different bias is applied just to see the transfer and output characteristics. And when we apply the gas, you can see this is without the exposure of gas. And when gas is put around 500 ppm of NO2, it goes down very fast. So conductivity, you can say here, is decreased with the increase with the interaction of the gas on the surface of MOS2 layer. And these are a variation with the concentration of gas. This is with 500 ppm, 100 ppm, 50 ppm. So that means more and more concentration of gas is there, more and more decrease in the conductance is obtained. And these are the calibration graph with NO2 concentration, you can see. And here the shift in the threshold current also you can calibrate as a function of NO2 concentration. The choice is either you can go ahead with the conductance, or you can go ahead with the threshold voltage as a function of NO2 concentration, and we can obtain the gas sensing response. These are the study with one, or you can say, monolayer of MOS2. Similar response has been, similar characteristic has been studied with 4 layer of MOS2, and with 4 layer of MOS2, response was found to be much better as compared to the single layer. We also tried with the 10 layer of MOS2, but the response was degraded. So ultimately what we found that 4 layer of MOS2, 4 layer gives a much better response as compared to your conventional your 10 layer or mono layer of MOS2. I can skip this part quickly now because time is running out. So these are the, just you can say, the repeatability of the experiments and the selectivity, which ensures that the response is much higher for the NO2 gas as compared to the ammonia, CO2, CH4, whereas we use the very high concentration of other gases, 200 ppm, and only very small concentration of NO2, 5 ppm, which clearly shows that these sensors are highly selective to the NO2 gas, not the other one. Then I want to spend just 5 minutes or 2-3 minutes on this nano generator. Same MOS2 layer we try to make for energy harvesting application, where you can just, by the friction, you can say the ocean or rainwater is there. If rainwater is there, you can put this MOS2 device in the rainwater, and that rainwater can be converted into the electricity. Alternatively, this system can be put into the ocean, and because of the waves, ocean wave, if they are going to interact with the surface of MOS2, then after that, you can generate the electricity out of it. So I can skip this part quickly. I can skip this part, and you can see here, this is a structure which we made MOS2-1, and on the surface of that, this NaCl droplet is just passing through. And when this droplet is passing through, this is the current you can say, open circuit voltage here, around 8 volt is generated, or this amount of current is generated out of it. And the system is repeatable. More and more drops is moved. So this is a response which we got. And we connected here the resistance, the load, and with the load, you can say how much we can generate the power out of the rainwater, or you can say the NaCl droplet. And then we try to make the systems on different substrate, SiO2, sapphire, silicon nitride. And we got the maximum response, the maximum voltage, and maximum current, or you can say the maximum power in the case of silicon nitride. And the resistance was found to be less in the case of silicon nitride. That means more and more resistive substrate is there, more and more possibility of generation of electricity is there. So these are the characteristics of this MOS2 on these different substrates. And these are the NaCl. We change the NaCl concentration, and we change in NaCl concentration also, you can see the response is almost flat, and maximum response is obtained with silicon nitride substrate. We try to change the slope angle, at which angle the energy generation or voltage is more. We found at 60-degree angle, the generation of voltage is much higher as compared to the other angle, slope angle. So this is a mechanism. I am skipping this mechanism part. Then we try to do one experiment that we put the NaCl in some beaker and we shake it by using the shaker, and by shaking it in this case, and you can say when your this is going up and down in both the sides, we are generating the voltage going up and down. It clearly shows that this device can be used for practical applications, and by using the number of layers, if monolayer is there, generation is more and more, and if you are increasing the number of MS2 layer, your generation, the current and voltage of power is going to decrease. I think I can stop here. These are the new materials. There's no need to go into the details. So thanks a lot from my side. I will be happy to give answer the few questions, if any.
So before handling the queries of the participant, I would like to thank our speaker, Professor Vinay Gupta sir, for taking out his valuable time to deliver a wonderful talk. Thank you, sir. Thank you so much for sharing the wide spectrum of knowledge. So, sir, here are some queries from the participants. Ritik Sharma has asked, could you please elaborate on the career mobility?
Definition of mobility, or what you want?
I think he want to just want to elaborate the career mobility.
Carrier mobility is the charge carriers are there in the semiconductor holes and electrons. How is they can move through the material. So if there is no defects, if there is no grain boundaries, in that case, the carrier mobility is very high. And if carrier mobility is very high, this transistor can use as a very fast switch. Generally in communications or digital electronics, all your 1 and 0 depends upon how fast your transistor is switching. So if mobility is high, that is very important parameter. More and more mobility is there, more and more you can say faster your switching will be. So ultimate goal is that the mobility should be as high as possible. This is a material property. And in material, if defects are minimal, the carrier mobility is very high. So 2D materials have the advantage that the carrier mobility is very high in general if there is no defects. So you have to reduce the defects so that mobility can be increased enormously.
Okay, sir. Next question is from Dr. Shailendra Jha, sir. How will these outstanding material you have meticulously researched change the technical life of general people in our society?
Please repeat the question.
Yeah. How will these outstanding materials you have meticulously researched change the technical life of general people in our society?
Actually, I'm not able to understand the question clearly. So this material is, I will say, is very good. But I think the question is how this material is very good.
Yes, sir. And it changed the technical life of general people in our society.
Yes. Because if you see the first slide where I have shown the Moore's law, we are going through the miniaturization. And when we are going to the miniaturization, now our, you can say the phone, the smartphone is powerful as good as laptops. All your activity can be performed in the smartphone. Along with that, you can do the communication. Multifunctionality is there. So that means how it's possible? It's possible only because of number of transistors which are available in the smartphone. And these transistors are miniaturized. Miniaturized means size is less, but functionality is more. And they can switch at very fast speed. Okay. So generally people were using silicon and gallium nitride or gallium arsenide based transistors. Now when users are greedy and we want more and more advantage of this material, ultimately we have reached the saturation limit of exploiting this material. That means to further decrease the size, we have to change the technology, and people have gone from planar to the 3D geometry with the same material. In 3D geometry also saturation has been reached. So now what is the further solution? The further solution is search for another material where the same functionality can be obtained with small quantity. And for those applications, 2D materials is the upcoming field where the same functionality can be obtained by monolayer. Monolayer means 0.6 nanometer I am talking about, 0.6 nanometer. Whereas in silicon, or you can say in gallium nitride, at the moment people are going with 5 nanometer. Below 5 nanometer it's not possible to go with silicon and gallium nitride. With MOS2 or with 2D material, you can go less than 1 nanometer. So that's the advantage which people are looking for. And that will going to change. You can say the smartphones are going to be much, much smaller, what are we are seeing at the moment, along with more functionality.
Okay, sir. Next question is from Dr. Ajay Pratap. Does these TMDs are suitable candidate for topological insulators?
Yes, not TMD, but the oxides are more suitable. I will say, but people are working on this transition metal oxides also, transition metal chalcogenides also.
Okay. So next question is from Ritvik Sharma. Is PLD technique most commonly used among the other newly introduced methods, or is it some other method?
Generally, for 2D materials, people are using the explanation where they're using the Scotch tape and they're putting on the bulk material. They're removing the Scotch tape. With Scotch tape, one layer comes out and they transfer this layer to the other system. But in this case, continuous layer coming out is very difficult and quality of the material is poor. Second alternate technique which people are using is chemical vapor deposition. The PLD is very less explored. So that's why we are focusing here. Why can't we use the PLD? And with PLD, we have demonstrated that you can grow large area deposition with controlled thickness and controlled stoichiometry and uniformity. So that's why PLD has an advantage over the other two techniques at the moment. Maybe in future new technique may come out, but only these three techniques are there till date.
Okay, thank you, sir. Next question is from Brij Mohan. What is the reason of high carrier concentration in TMDs?
What is the reason of high concentration?
Yes, what is the reason of high carrier concentration in TMDs?
Transition metal chalcogenides. They are semiconductors. Actually, high concentrations are in the graphene, not in the TMCs. The carrier concentration is much, much higher in the case of graphene. The previous one, the category, the carbon category. The TMCs comes under the category of semiconductors. So carrier concentrations are not as high as in the case of graphene, but in the case of graphene, the band gap is 0. So you can't make the transistor as a switch by using the graphene. By TMC, transition metal chalcogenides, the band gap is finite and they are semiconductor. Mobility is good, carrier concentration is good, not high, but good. So you can make the transistor as a switch. So that's why TMCs are important as compared to the graphene.
Okay, due to paucity of time, I can take only the last question. That is from Ruchika Joshi.
Otherwise, you can send me by email, we'll reply. Yeah?
Yes, sir. Yes, sir. Sir, last question is from Ruchika Joshi. How can we minimize the mismatching of film and substrate?
by using the alternate buffer layer. That's the very common phenomena people are using. So because substrate is just a platform to deposit a material. So if lattice mismatching is very large, then you choose a material, the buffer layer, which can first grow on the previous substrate whose lattice matching is close to the material which you want to grow. Okay. So you have to choose that material, intermediate material, whose lattice mismatching should be minimal with respect to the material you want to grow. So that's the only, you can say, the better choice to reduce the lattice mismatch. For example, I will give you the example. If on silicon, if you want to deposit the gallium nitride, then we try to deposit the aluminum nitride as a buffer layer, whose lattice matching is good, and aluminated growth on silicon is good.
Okay, so there is one more question. Why MoO2O3? Why
MoS2.
MoO3 is not used as a channel material for FET?
Can be used as insulator. MoO3, the band gap is wide, not as small as MoS2. So you have to tune the band gap in that case, because the band gap is more. In that case, the behavior is more close to the insulator, not the semiconductor. Either you have to create the intrinsic defects to use as a channel in the case of MoO3, or you have to do extrinsic impurities. The band gap of MoO3 is more as compared to MoS2.
Okay, so that's all. Thank you so much, sir, for handling all the queries of the participants and sharing your wide spectrum of knowledge about NoS2 as a unique material.
Hello.
And in case participants have more queries, they can directly mail to Professor Vinay Gupta, sir. We will share his email ID in the chat box.
Yogesh.
Yes, sir.
I just wanted to speak to Professor Gupta.
Yeah.
If he's
please,
still there.
Please.
Yeah, I'm here.
Professor Gupta.
How are you, sir? Yeah,
I'm fine. I just wanted to know that, MoS2, I suppose, has, as you said, is the hexagonal closed peg structure. Is that so?
Yeah, in two-dimensional, that means in X and Y, you can say plane, the covalent bonds are in the form of hexagonal. And in vertical directions, they are interacted with the van der Waals.
Yeah, that is true. So, in between MoS2, if you have a single layer, we have a tetrahedral void in between, where the MO atom is placed between two sulfur atoms. Is that so? And then when we deposit another layer of MoS2, then we have an octahedral void between the two, and there we have the van der Waals bond.
Yes.
Has it been? Have you already? Has some study been made to make a to introduce a dopant between two layers within the octahedral void? If we place a cation which is of much smaller radius than the octahedral void.
No. At the moment, no doping has been done, because what people are doing at the moment, they are using generally the explanation. Explanation means they are taking the bulk material and then they are just removing the layer by layer. At the moment, they are doing that. And to incorporate the defects in such kind of formation is difficult. But now, since you have the PLD, and with PLD, you are growing the material, people will try now. I think they can use this technique to dope the material inside and to study.
Yeah, that's what I'm trying to convey, is that how does it affect the, if we dope a material between the two layers in the octahedral void, how is it going to affect the conductivity of that?
The first thing is that how it's going to change the bonding structure, because probably when you're going to dope something in between the two layers, might be, it's my guess, they can make the covalent bonds. And if they can make the covalent bonds, they will lose the inherent property of the 2D material. So that's the biggest challenge probably. That's why people are not trying at the moment, because they want to explore first the 2D material itself.
Yeah, okay. Right, sir.
Okay.
Thank you so much, sir, for enlightening the session. And there is one announcement that we have another hands-on session at sharp 2 p.m. So you are requested to join the session on time. Now I would like to hand over the session to Dr. Deepti Goyal for the further proceeding. Deepti Goyal, ma'am.
Thank you, sir. Thank you, sir. Thank you. Learn from yesterday, live for today, hope for tomorrow. The important thing is to not stop questioning. So this is a saying by Albert Einstein. So on behalf of Physics Department, I hope that our inaugural session will definitely prove to be a good start for our 2-day online national seminar series and will be followed by effective, productive, and successful interaction in a positive and stimulating atmosphere. So there is a break session now and we shall all join at 2 p.m.
Thank you, everyone.
Thank you.
So now we can end the session.
Yogesh sir, you don't end. It will be ended by Monica ma'am.
Okay, fine.
Thank you all. Thank you, sir.
Thank you. Monica ma'am is here.
बस मैं उनको कॉल कर रही हूँ.
Okay.